Welcome to the lecture on factoring. There are many different ways to factor polynomials, but the first method that you always want to use and check for is greatest common factors. So what that means is you're going to look at your polynomial and you're going to try to find the GCF, the greatest common factor that divides evenly into each term. So if we have this example here, what we would want to look at is term by term. Are there any numbers that divide evenly into 125, 60, and also 85? And in this case, since all the numbers end in either zeros or fives, we know that at the very least 5 divides into each of those 3 coefficients. If you check some of the other numbers, like for example 85, 85 is 5 times 17. Since 17 doesn't have any other factors and it obviously doesn't go into 60 or 125, then it looks like 5 is going to be our best choice for our greatest common factor. So that would be the number part. What we'd want to check for next are the A's. How many A's do each term have? We've got 3 here, 4 here, and 5 here. When you're factoring out variables, you want to always pull out the variable raised to the smallest power, the power that they each all have. So in this case, that would have to be a cubed. So my GCF is also going to include an a cubed. And if we look at the z's, I have z to the 5th, z to the 4th, and z squared. The smallest power that they all have is z squared. So I'm also going to pull out a z squared. So my GCF is 5a cubed z squared. Now when we pull that out, what we're going to do is write in parentheses what is left over. So if you divide 5 into 125, you get 25 back. If you pull out all these a cubes, then no a's are left. If I pull out 2 z's, and I had 5 originally, then that means I'm going to have 3 z's left, or z cubed. Remember that if you wanted to double check, you could always redistribute this back across. 5 times 25 is 125. A cubed times no more a's is going to stay a cubed. And z squared times z to the 5th, or z squared times z to the cubed is z to the 5th. So we know that we've done this correctly so far. Now we're going to go to our next term. There was a plus in front of it, so that's going to stay in my parentheses. 5 divides into 60 12 times. If I pull out an a cubed and I had 4 a's to begin with, then I'm going to have 1 left. So an a to the 1st, or just a. And if I pull out a z squared and I have 4 z's to begin with, then that means I'm going to have 2 z's left. Then I have a minus. 5 divides into 85 17 times. If I pull out an a cubed and I had a to the 5th, then that means I'm going to have 2 a's left, so a squared. And if I pull out my z squared, then this is all gone and there's no z's left. So if you want to double check, you could redistribute this 5a cubed z squared to each term, and you should always end up with the original problem that you started with. This does check out correctly, so here's our final answer. Okay, so let's try the next example. If we look at these two terms, what number goes into both? And you will probably need to do a little trial and error on your calculator unless you're real familiar with the factors of 38. 38 is 19 times 2, so that means 19 goes into both of these. So I'm going to pull out a 19 from both terms. I have a p squared here and a p squared here, so I'm going to pull out p squared from both. Then I have a y here and a y cubed here. The smaller power is the y to the 1st, so we can only pull out 1y. So in parentheses, we're going to write what's left over. Now notice on this first term, I pulled out the 19, I pulled out the p squared, and I pulled out the y, so it doesn't look like there's anything left. It would be incorrect, however, to put a 0 here, because remember, if we redistribute 19p squared y times a 0, would give you back 0, not 19p squared y. So the 0 is wrong, and instead what we're going to have left is a factor of 1. Since 19p squared y times 1 will get me back the original 19p squared y. So if you factor out everything, you're always going to be left with a factor of 1. Then we have our minus. 19 divides into 38 2 times. I pulled out all of these p squareds, and I pulled out one y, and I had 3, so that means I have 2 y's left. And if I were to redistribute, I'll get back that original term. So here's our solution. On the next example, we have negative exponents. There's no number that goes into both of these terms since this coefficient out front is a 1. So the only thing I can pull out are some k's. And if we use our rule that you want to take out the smaller power, negative 2 and negative 4, if you compare those, the smaller power is negative 4 because it's more negative. So in this example, we're actually going to pull out k to the negative 4. And if I do that, since in this first term I had k to the negative 2, I didn't pull out exactly the same amount, so there should be some k's left over. So how many k's are left? We put a little question mark here. Negative 4 plus what would get me back to a power of negative 2? Because remember, when you redistribute, these exponents should add. So negative 4 plus what would be negative 2? It's got to be positive 2. Negative 4 plus 2 is negative 2. So that means what I have left over is k to the negative 2. So that negative 4 plus, k to the negative 4 times k to the positive 2 gives me back k to the negative 2. Okay, on the next example, or on the next term, I have that plus, I have that 2 left over, and I pulled out all of these, so there's no k's left over. So my final answer, k to the negative 4, k squared plus 2. So remember, always redistribute back to check, especially on these negative exponents, trying to figure out what is left over. And you want to add exponents when you redistribute. Now the next example looks quite a bit different than the ones we've done so far because we have these parentheses in the problem. But if you notice, this problem is kind of special because what's in the parentheses happens to be exactly the same for both of these terms. So we're going to treat this stuff in parentheses just like a GCF, a greatest common factor. So I am going to pull out the quantity 1 minus 4p, and in parentheses we're going to write what's left over. Now in this first term, which is all this stuff before the minus sign, I pulled all of that stuff out, so all I have left is the 3p in front. Then we have our minus. In this second term, I pulled all of this out, so the only thing left is a 2q. So here is our solution. Okay, so that's factoring, looking for a GCF, a greatest common factor. You always, always, always want to check for that first in any kind of factoring problem. Once you've pulled out a GCF, it'll give you a much simpler polynomial to deal with. That may still factor further, but at least it'll be easier and the numbers will be smaller to work with. So always check for a GCF first. If you've pulled out a GCF, or if there is no GCF, then you need to rely on some other different possible ways of factoring. And the first new method that we're going to talk about is called grouping. And this is a method that you want to try whenever there are 4 terms in your original expression. This could also work for any even number of terms. So if you had 4 terms, 6 terms, 8 terms, 10 terms, grouping is always a good method to try. So here's how grouping works. It's kind of like GCF factoring, except instead of pulling a GCF out of all 4 terms, we're going to group together the first 2 and pull out a GCF, and then we're going to group together the second 2 and pull out a GCF, and then you'll see what happens from there. So if we look at these first 2 terms, what do these first 2 terms have in common? They both have an m. So if I pull that m out, then what's going to be left goes in parentheses. I took away one of these m's, so one m is still left. I took away this m, so a plus 2 is left. If I go to the next pair of terms, what do they have in common that I could pull out? Well, they both have an n. So if I pull out an n, then this n is gone and I have m left over. This n is gone and I have a plus 2 left over. Now in this grouping method, there are really 2 steps. We've just done step 1, where we grouped together the first 2, pulled out a GCF, grouped together the second 2, pulled out our GCF. And if you've done this correctly, In most grouping problems, what you'll be left with are identical expressions in these parentheses. So we're going to treat this just like the last example we did, where this m plus 2 is like a GCF that I can pull out, and in parentheses, when I take these two away, what's left is the m plus the n. So it's a two-step process of factoring. First, pull out the GCF from your first two and your second two, and if you've done it correctly, what's left in those parentheses should match, so you can factor that out further. Okay, let's try this again. Here's 4 terms, 1, 2, 3, 4, so grouping is a good method to try. If I group together these first 2 terms, what do they both have in common? Well, they're both divisible by 3. So I'm going to pull out a 3. 3 times 2 would get me back to 6, and if I pull out this 3, then I'm left with a minus x. Now on the next 2 terms, these two right here, they both have a y, so I could pull out a y. Now initially, if I just pull out the y, then I'd be left with a negative 2 and a plus x. And this isn't quite what we want, because if you compare what's in the parentheses here to what's in the parentheses here, they are almost the same, but they're opposites. The signs are backwards. So an easy way to fix that is, instead of factoring out just y, we can factor out a minus y. And if we pull out the minus and the y, then we'll just be left with positive 2. If we pull out the y and a minus, then I'm going to need a minus x, so that when I redistribute, I'll get plus xy. So now what's in these 2 sets of parentheses match exactly. So I can pull it out like a GCF, and what's in parentheses after these 2 are gone is 3 minus y. Okay, now this last example of grouping is a little bit more challenging. If you first start your grouping problem, first recognize to use grouping because there are 1, 2, 3, 4 terms. So your first instinct might be to group these 2 together. They both have a b in common, so I could pull out b. If I do that, I'm going to be left with a 4 and just a b squared from the first term. And if I pull out this b, then I'll be left with a squared. But when I go to the next term, both of these have a negative and an a, so you might be tempted to pull out a negative 4a from each of these. And that means from this, we'd pull out the negative, the 4, and the a, only thing left is a 1. And here, if I pull out the negative and the a, oops, I can't pull out a 4. Back up here a little bit. We can't pull out a 4 because this first term didn't have, the last term didn't have a 4. So let me recopy that problem correctly. We had a minus 4a minus ab to the 4th. This term over here doesn't have a 4. So we can't pull out the 4, but we can still pull out the minus and the a. And that would leave us with 4 plus b to the 4th. Now when you group the first 2 and the last 2 like we did right here, this doesn't seem to be working for us because what's in the parentheses here does not match what's in the parentheses here. So grouping doesn't seem to be something we could use in this particular example. However, we're going to be a little bit more creative and still make it work. Since we have 4 terms, I'm going to try grouping, but I'm going to erase all of my work that I had here before, and instead we're going to rewrite the problem by rearranging a couple of terms. And in this example, I'm just going to swap these 2 terms right here. So I'm going to rewrite the problem. I'm going to leave 4b cubed where it is, but next I'm going to put minus 4a, and then the plus a squared b, and then on the end that minus ab to the 4th. So all I did was switch these 2 terms around, which we can do because addition is commutative. So if I try that, let's try our grouping now, grouping these 2 together and these 2 together. The first 2 terms here, the only thing they have in common is that 4, so let's factor out 4. That'll leave us with b cubed minus a. And if I go to my second 2 terms, what they have in common is they both have a's. I have an a squared and an a to the 1st, so the smaller power would be an a to the 1st. and then I have a b to the first and a b to the fourth, so the smallest power there would also be a b to the first power. So I'm going to pull out an a and a b. So if I pull out an a and a b, this b is gone, one of these a's is gone, so one a is left. If I go to this term, I pulled out this a, one of these b's is gone, so I have the minus and a b cubed left over. So now compare what's in the parentheses. We have b cubed minus a here, and a minus b cubed here. We're almost there, right? We've almost made it to what we want because these are almost identical. The only problem now is they are opposites. So how do we fix that? How do we change the signs really easily? Well, we change this plus to a minus, and we factor out a negative so that this a becomes minus and this b cubed becomes plus. So all we've really done there is basically change our signs. We now have a minus a and a plus b cubed. And remember that b cubed minus a is the same as negative a plus b cubed because, again, addition is commutative, so we can swap the order around here. Alright, so I think we are all set to finish the problem. Since this matches this, we can factor it out, and you can factor either order, doesn't really matter. I'm going to factor out the b cubed minus a, and if I pull that out, this is gone, so I'm left with 4 minus ab. So this example a lot more challenging than the other two because when we initially tried grouping it didn't seem to work. So what we need to do in that case is rearrange a couple of terms. Usually I find that just swapping the second and the third term around so that they are in a different order will usually make the grouping problem work correctly. So try swapping terms around, then do your grouping process, and remember you always want what's left in these parentheses to match what's left in these parentheses. And then you can pull it out and you're left with your final solution. Okay, so that's the grouping method. You want to try that whenever you have 4 terms or really any even number of terms, but most commonly you're going to see it with just 4 terms. Okay, so we've got GCF factoring, we've got grouping factoring, and now we're going to move to reverse FOIL factoring. So reverse FOIL is just like the FOIL process you learn when you distribute, but going in reverse. And the types of problems you're going to use this for is whenever we have 3 terms to begin with. Not 4 terms, but 3 terms. And this reverse FOIL process kind of breaks down into 2 cases, the easy case and the hard case. So we're going to do the easy case first because this is the case where the coefficient is 1 for that leading term. So wherever you see that x squared term, for example, that leading coefficient here or here has to be a 1. If it is, then we can use our reverse FOIL fairly easily. What we're going to want to do is take our trinomial, this has 3 terms, 1, 2, 3, and we're going to break this up into a binomial times a binomial. And the way we're going to make this work is we're going to say, okay, what 2 things have to multiply to give me that x squared in front? Well, that has to be x times x. What 2 numbers have to multiply to give me 12 on the end, and at the same time they have to add to positive 7. So we have to think of 2 factors of 12 that add to 7, and the obvious choice there would be plus 3 and plus 4. And if you check this, if you FOIL it back out, first times first would be x squared, outer times outer would be 4 times x or 4x, inner times inner would be 3x, and last times last would be 12. And so it's these 2 middle terms that are adding to that 7x that we were looking for. So we know we did this correctly. So my solution is x plus 3 times x plus 4. It would also be correct to write this as x plus 4 times x plus 3. It doesn't matter which factor you write first. Okay, so for the easier case of reverse FOIL, you use this when the leading coefficient is a 1, and the process here is you set up your 2 sets of parentheses, We need two things that multiply to x squared, which are going to always have to be x times x. And then we want two numbers that multiply to the constant on the end and add to the middle term. So in this problem, we want two numbers that multiply to negative 28 and at the same time add to negative 3. So two factors of 28 are 4 times 7, and those two numbers have a difference of 3. So let's try 4 and 7. I would want the 4 to be plus and the 7 to be minus because the middle term is negative, so the larger number over here needs to be negative as well. So double checking, positive 4 times negative 7 is negative 28, plus 4 and minus 7 add to negative 3, so we did this correctly. X plus 4 times x minus 7. Okay, so when the leading coefficient is 1, you want two numbers that multiply to the constant on the end and add to the middle coefficient. The harder case of reverse FOIL is when that leading coefficient out front is not a 1, because then it's not so easy to identify what factors are going to make this work. And unfortunately, there's no really set way that's always going to work for you. We have to use trial and error on sort of this harder case. So the harder case again is when the leading coefficient out front, which in this case is a 6, is not a 1. So if it's not a 1, we're still going to set up our two sets of parentheses, but now we need to think of two things that multiply to 6x squared. And there's more than one way to get 6. We know we need x's, but to get the 6 we could do 2 times 3, or we could do 6 times 1. So that's why we're going to have to do some trial and error to figure out which one of those two choices is the one to use. At the same time, to make it even more difficult, we need two numbers that multiply to 14. 2 times 7, 14 times 1, and out of all those combinations, we need to get a middle coefficient of negative 5. So again, it's really trial and error trying to figure out which combination of factors of 6 and which combination of factors of 14 is going to give me that right middle term. So how do you handle this? Well, what I like to do is fix one of my factors. So for example, if I want to get 6, you could either do that with 2 times 3 or 6 times 1. Pick one of those choices and just go with it. If it doesn't work out, then you're going to erase your choice, your original choice, and change it to the other one. So in this case, I'm going to try 2 times 3. I'm going to say that to get 6, I need 2 times 3. If this doesn't work, we'll have to erase it and change it to 6 times 1. Now, to get the 14, there are two ways to do that, but because of the way I've chosen the order of my 2 and my 3, we have to consider both orders for getting 14. So by that I mean I could do 7 times 2, but that might give me a different middle term than 2 times 7. So we have to consider both possible orders. I could also get 14 with 14 times 1 or 1 times 14. So you kind of make a little list for yourself of all the ways to get 14 in both orders. Now, how do you find out which one is the correct one? Well, we have to check that middle term. We're trying to get a negative 5 in the middle. And the way you get your middle terms from FOIL is from the outers multiplied together and the inners multiplied together. So we're going to do that here and see which one is going to give me a negative 5. So for example, I would take this 2 times this 2, that's 4, or 4x actually, and then I would take this 7 times this 3x, and that would be 21x. Is there any way to get a negative 5 from a 21 and a 4? No. So that means this choice doesn't work. So now what we're going to do is erase down here, and we're going to try this again with our next outer and inner choices. So I'm going to do 2 times 7, which is 14, and 2 times 3, which is 6. Is there any way to get negative 5 out of that? No. So that choice doesn't work either, so I'm going to cross it off. And then we erase and we try again. So this is kind of a tedious process, but unfortunately there's really no shortcut. You just want to kind of be lucky with your choices. If we try 2 times 1, that would be 2. 14 times 3 is going to give me a 42. 42 and 2 do not give me a 5 at all, so that choice doesn't work. Okay, let's try our last choice down here. So if we do 2 times 14, that's 28. If we do 1 times 3, that's 3. Again, 28 and 3 is not going to give me a negative 5. So, what do? This didn't work. Well, did we consider every possibility? We did for the 14s, but we did not consider every possibility for getting 6. So remember, if your choice of 2 times 3 didn't work, then you still have to go back and change how you got 6. So I could change this to 6 times 1. That's another way to get 6. You don't need to change your list of ways to get 14. They will still apply, but we're going to have to go through these lists and see if we can get that negative 5. So, for example, I'm going to take 6 times, let's do 6 times this 2. So 6 times 2 is 12, and 7 times 1 would be 7. And there it is. A 12 and a 7 can get me a 5 if I subtract correctly. So I want a negative 5. That means the larger of these two middle terms needs to be negative. So I want the 12 to be minus. The 12 is coming from this 2, so I need to make that 2 minus. I want the 7 to be plus, and the 7 is coming from this 7 up here, so I want to put a plus sign there. So let's clean up our answer. This is what we came up with. 6x plus 7 times 1x, or just x, minus 2. And just verifying here, we get plus 7 times minus 2 is the minus 14. 6 times 1 is the 6x squared. And the inners would be 7x and negative 12x, which give me negative 5x, and that's what I wanted. So this is the correct answer. Whew, that took a long time. There were lots of choices there, so you can see why this is the much harder case. You have to do it by trial and error. There's really no shortcut, and the only way to make these less work is to hope that you pick the correct choices the first time round instead of having to run through every single possibility. Okay, so let's try another example. Now when I look at this next one, something should look a little strange to you. First of all, we've got these higher powers of z's, and in these trinomial problems where we have 3 terms, 1, 2, 3, and we're trying to use the reverse FOIL like we've been doing on these last examples, we only saw x squareds. So these powers on the z's seem a little bit high. So that's kind of a little clue to you that maybe there's a GCF involved. Another clue would be that we have 32, 20, and 12 for coefficients. All of those are even, so at the very least we should be able to pull out a 2. So this problem has a GCF that we're going to need to pull out first. Okay, so what's the biggest number that divides evenly into 32, 20, and 12? If you know your multiplication tables pretty well, then you'll know that 4 goes into each of these. So I'm going to pull out a 4. And for the z's, I have z to the 5th, z to the 4th, and z cubed. Remember, you can pull out the smallest power of z that they all have. So my GCF is going to be 4z cubed. So what's left in parentheses here? 4 divides into 32 8 times. If I pull out 3 z's, then I have 2 z's left. Minus 4 goes into 20 5 times. If I pull out 3 z's and I had 4, then I have 1 z left. And finally on the end, 4 goes into negative 12 minus 3 times, and I pulled out all of these z cubes. So here's my trinomial. Now when you're factoring, especially when you're doing it with a GCF, don't stop here, because what's in parentheses may be something that could factor further. And this is a trinomial. It has a leading coefficient which is not a 1, so it's going to be this harder case, but we need to try reverse FOIL and see if it's going to work or not, see if we can factor it. So what do you do with the GCF out front? Well, you just leave it there. Don't forget about it, it's still there. And then for this trinomial, we're going to write down our 2 sets of parentheses. We need 2 things that multiply to 8z squared, and 2 things that multiply to 3. Well, I like to place my variables in first. I know that I'm going to need a z and a z. I'm going to leave a little space in front, because that could either be 4 times 2 to give me 8, or it could be an 8 times a 1. On the other side, I have a 3 to get to, and that one only has one choice. The only way to get 3 is 3 times 1. So if you only have a one choice, I usually fix that choice, 3 times 1, and that means in these other 2 spots over here, I need to list all the ways that I can get 8. So that could be 4 times 2, or 2 times 4. Notice I'm using both orders because I've already fixed the particular order of my 3 and my 1. The other way to get 8 is 8 times 1, or possibly 1 times 8. So here's our list, and we're going to have to check each of those cases. So we're checking our outers and our inners. So we're going to take this 4 times 1, which is 4, and 3 times 2, which is 6. Can I get 5, negative 5, out of 6 and 4? No. So that means this choice doesn't work. So we erase and we try again. Go to the next choice on the list. So now we're going to go to 2 times 1, which is 2, and 3 times 4, which is 12. Can I get a 5 out of that? No. So that choice doesn't work either. So we move down our list. And if we go to 8 times 1, that'll be 8. And if we do 3 times 1, that'll be 3. 8 and 3 do have a difference of 5. I want to get a negative 5, so the larger number here needs to be negative. So I'm going to make the 8 negative. The way I'm getting that 8 is from this 8 out front times the 1. So to make it a negative 8, I'm going to make that 1 minus. And I want the 3 to be plus, so I'm going to put a plus sign in front of my 3. So let's clean up our solution here so we can see what our final answer is. The final answer was the 8z plus 3 times 1z, or just z, minus 1. And you can double check. 8z times z was 8z squared. 3 times negative 1 was the negative 3. And in the middle we had plus 3 and minus 8, which is that negative 5. Now don't forget about that GCF that was out front. That is still there. So we're going to bring it down in front of our other 2 factors. And here's our final solution. So if you have 3 terms, the factoring method to use is called reverse FOIL. It's just doing that FOIL process backwards. If the leading coefficient is a 1, then it's much easier and you don't have as many choices to run through. If the leading coefficient is not a 1, then you have to make lists of all your possibilities and go through the list one by one until you find the combination that works. So it's much harder. Okay, the next factoring method that we're going to talk about is actually 2 different formulas that we're going to discuss, and they both are going to apply, or you're going to try using them whenever we have just 2 terms. Okay, so instead of having 4 terms, which was grouping, 3 terms, which was reverse FOIL, if we have 2 terms, then there's going to be 2 choices that we could try. We might have what's called a difference of squares, or if we have 2 terms, we might have a sum or difference of cubes. So here's what you have to look for. First of all, you have to have 2 terms. In the difference of squares pattern, you must have these two terms being subtraction. So there has to be a minus sign between them. If there isn't a subtraction symbol, then nothing can be done and it won't factor. Okay? So we need a minus sign, and then the two terms on either side of that minus sign need to be perfect squares. If they are, then we're going to basically kind of take a square root of them, and that's what's going to go in our parentheses, but the signs are going to alternate because in a difference of squares pattern there's no middle term. So the only way to make that middle term cancel out is to have the identical expressions in our parentheses but with opposite signs. So for example, if we saw 4x squared minus 9y squared, first of all we have subtraction between two terms, so difference of squares is a good candidate, and 4x squared is a perfect square, it comes from 2x, and 9y squared is a perfect square, it comes from 3y. So this is a difference of squares, so all we have to do is write down our two sets of parentheses. The way to get 4x squared is from that 2x and that 2x, that square root, and the way to get 9y squared is from a 3y and a 3y. And to make sure that we end up with no middle term, because the original problem didn't have a middle term, one of these has to be plus and one of these has to be minus. It doesn't matter which one is which. And here's our solution. So the difference of squares pattern, it's really easy to use as long as it applies. Okay? In this next example, we have x to the fourth minus 1. We only have two terms. There is subtraction in between. X to the fourth is a perfect square because it's an even power. The square root of x to the fourth would be x squared. And 1 is a perfect square because the square root of 1 is just 1. So we can use our difference of squares pattern on this. To get x to the fourth, we need x squared and x squared. To get 1, we need 1 and 1. One of these has to be plus, one of these has to be minus, so that we have no middle term. Now, this is kind of a trick question because we're not actually finished yet. If you look at this, one of these factors can be factored some more. Which one is it? It's going to be the minus case only, because if you look at the minus case, there's a difference. X squared is a perfect square, 1 is a perfect square, so this factor right here is another difference of squares pattern. So we can use this formula again and break this one up. We need x times x to get x squared, 1 times 1 to get 1, make one of these plus and one of these minus so we have no middle term. Now how come this one over here doesn't work? The only reason it doesn't work is because it's a sum of squares and not a difference of squares. There's no way to make this factor if you have addition in between. So when you write your final answer, don't forget about this factor. It's still there, so you want to make sure you bring it down. And your final answer has all three of these. And there's our solution. So just remember that whenever you're factoring using whatever method at all, always check your factors and see if they might possibly factor some more, especially if your original problem is starting with a power that's higher than 2. In that case, you usually can factor a couple of times, but it might require different methods. Okay, so that's called your difference of squares pattern, when you have two terms being subtracted and the two terms are perfect squares. Another option to try if you have two terms is a sum or difference of cubes. So this time we are allowed to have plus signs or minus signs in between our two terms, but you need to have perfect cubes instead of perfect squares. And the way you factor this is a little bit more complicated. In the first factor, you take your cube roots. So whatever was in this first spot, take the cube root, and that goes in your first factor. Whatever was in the second term, take the cube root, and that goes in the second position. The second factor is actually a trinomial. It's going to be whatever you put here squared, whatever you put here squared, and the middle term is these two multiplied together. And notice the signs alternate. So if you have a plus sign in front, your middle term will be minus. If you have a minus sign in the middle, then this will be plus. And how do you determine which case it is? The signs match. So if this is plus, your first factor is plus. If this is minus, your first factor is minus. So let's see how this pattern applies. When we look at this next example, I have two terms. There is subtraction, but 8x cubed is not a perfect square, so that's why a difference of squares won't work. 8 is a perfect cube, though. It's 2 cubed, 2 times 2 times 2. So we have 8x cubed, a perfect cube. 1 is also a perfect cube, so this is a difference of cubes. So the way the formula is going to work is we're going to have two factors. The first factor has 2 terms. The second factor will have 3 terms. To fill this out, you're going to take the cube roots of the terms you see. So the cube root of 8x cubed is 2x. The cube root of 1 stays 1, and since this was minus in the original problem, that first factor will be minus. Once you know these 2 terms in your first factor, then you're just going to use those to get the second factor. The first term here comes from your 2x quantity squared. So 2x quantity squared turns into a 4x squared. The last term over here comes from your 1 being squared. 1 squared stays 1, and that constant on the end is positive, always. Over here in my formula, it was always a plus sign. The middle term comes from these two multiplied together. 2x times 1 is going to be 2x. And the sign of that middle term should be the opposite of the sign you have in the first factor. So since we had minus, this middle term should be plus. So my final answer is 2x minus 1, parentheses, 4x squared plus 2x plus 1. And if you wanted to verify it, you could just FOIL it all out. All those middle terms cancel out, and the only terms you end up with are the first terms from the 8x cubed and the negative 1 times 1 to give you that minus 1 on the end. Alright, let's try this one more time. We have 125x cubed minus 27y cubed. So those x cubes and y cubes are kind of giveaways that this is probably a sum or difference of cubes. We've got a minus sign, so it's going to be a difference. And 125 is 5 cubed, and 27 is 3 cubed. So we have nice perfect cubes. So here's how we're going to factor it. 2 sets of parentheses. The second set of parentheses I'm making a little bit wider because we need to fit 3 terms in there. In the first position of the first factor, we take the cube roots. So the cube root of 125x cubed, that comes from a 5 and an x. Cube root of 27y cubed comes from a 3y, and this was minus, so our first factor is minus. In the second factor, you get those right from this first factor. So we take 5x and you square it, which would be 25x squared, and that's what goes in the first position. Then you take 3y and you square that. That's 9y squared. That's always positive. And the middle term is these two multiplied together. 5x times 3y is 15xy. And the sign of it is opposite from what you started with. So we have minus, so this sign is plus. So our solution, 5x minus 3y, parentheses, 25x squared plus 15xy plus 9y squared. Okay, on this last couple pages here, we've gone through every different type of factoring method that we're going to learn about. GCFs, grouping if you have 4 terms, reverse FOIL if you have 3 terms, and either difference of squares or sum and difference of cubes if you have 2 terms. And on these last examples, this is basically just a miscellaneous selection of problems, and the hardest part of all is deciding which method of factoring should you apply. So if we look at this first problem, 5x to the 4th minus 80, right away I see that there are only 2 terms, and it is subtraction. So if this is going to factor, it either has a GCF and or it is going to be a difference of squares or a difference of cubes. So if we look at our numbers here, 5 and 80, those are not perfect squares, and they're not perfect cubes either. So initially it may not look like it's a difference of squares or difference of cubes. However, 5 does divide into 80, so there's a GCF. So you want to always pull out your GCFs first, because what you're left with might be something that could factor. So here, if I pull out 5, I'm left with an x to the 4th, and 5 goes into 80 16 times. So now if you look at what's left, x to the 4th is a perfect square because it's an even power, and 16 is a perfect square, and we have a difference. So this x to the 4th minus 16 is a difference of squares. So we're not done factoring. Recopy the 5, put down your 2 sets of parentheses. I'm going to take square roots. So the square root of x to the 4th is x squared. I need both of those in the front. And the square root of 16 is 4. I need both of those in the back. One of these is plus, and one of these is minus. Now remember, this was a 4th degree, so sometimes with these higher powers, you may be able to factor more than once. We pulled out our GCF, we just did a difference of squares, but we might still not be done yet. If you look at these two factors here, the one with the minus is a square minus a square. So it's another difference of squares. So we're not quite done yet. We're going to break this last factor up into 2 more parentheses. Square root of x squared is x, so I need x and x. Square root of 4 is 2 and 2. Make one of them plus, one of them minus, and then we just want to make sure we bring down the x squared plus 4, which we couldn't factor because of the plus sign, and the 5. So our final answer, 5 x squared plus 4 times x plus 2 times x minus 2. So all of those should be in your final answer. So on these higher powers of x, be careful, you might have to factor several times before you get to your final answer. Okay, on the next one we have 4x squared plus 16. 4 and 16, right away you should see there's a GCF there. So if we pull out our 4, we're left with an x squared, and 4 divides into 16 4 times. On this x squared plus 4, it's really tempting to say that that's a difference of squares because they're both perfect squares, but we have addition. So be careful, we can't factor unless we have a difference of squares, and this is a sum of squares. So we can't really factor this any further. The only thing we could do to factor it is pull out that 4, that GCF, and the rest has to stay the same. So that would be our final answer. Okay, let's look at the next example. 12a squared plus 17ab plus 6b squared. Always, always, always check for a GCF first. Unfortunately here we don't have one because 17 is prime, so 6 and 12 or any factors of those aren't going to divide into it. So we don't have any GCF to pull out. If we don't have a GCF, then you want to count terms. We've got 1, 2, 3 terms, so if this is going to factor, we're going to have to do it by reverse FOIL. Unfortunately, our leading coefficient here is 12, not a 1. So this is the harder case, the trial and error case of reverse FOIL. So let's try this. Remember, this takes a little bit of practice and a little bit of time. In the front position, I need 2 things that multiply to 12a squared. So I know I need some a's, but in front of those a's I could do 3 times 4, I could do 2 times 6, I could do 12 times 1. There's lots of ways to get 12. In the second positions here, we need to get a 6b squared. So I know I need b's, and to get 6, I could do that with 2 times 3 or 3 times 2. So there's a couple choices for 6. There's a few more choices for 12. You're going to basically just have to pick one and go with it and hope that you got lucky and picked the right choice. So since 6 has fewer choices, I might try one of those and say, let's say 2 times 3 is 6. So I fix the position of the 2 and the 3. So that means in front of these a's, I need to list all the ways to get 12 in both orders. So that could be 4 times 3, 3 times 4, 2 times 6, 6 times 2, 12 times 1, or 1 times 12. There's going to be a lot of choices here. Hopefully one of these earlier choices will work. How do you check to see if it works? You check your outer terms and your inner terms. We're trying to get a 17 in the middle. So we're going to take 4 times 3, which is 12, and 2 times 3, which is 6. 12 and 6 don't give me 17. So that's not going to work. So now what I'm going to do is go to the next one, cross this off my list. Let's take 3 times 3, which is 9, and 2 times 4, which is 8. 8 plus 9 gives me 17. And if I want a positive 17, then I need both of these to be plus. So I need plus signs in both my parentheses. So we got it to work. Our solution is the 3a plus 2b times 4a plus 3b. Okay? Next example, we've got 3x to the 6th minus 14x cubed plus 8. Now the powers on the x's are a little higher than what we normally see when we have a trinomial, 3 terms. This one has 3 terms. So if we're going to factor this, we're going to look for a GCF first. Unfortunately, this one doesn't have one since 3 doesn't go into 14 or 8. So the only thing left to try is reverse FOIL because we have 3 terms. Don't let these higher powers of x bother you. We'll make this work. So in my parentheses, my 2 sets of parentheses, I need 2 things that multiply to 3x to the 6th and 2 things that multiply to 8. Since there's only one way to get 3 times 1, I'm going to fix that. And think about how do you get x to the 6th. Look at your middle term. The variable that you see on that middle term is exactly the variable we're going to need next to that 3 and that 1. I need an x cubed times an x cubed to get me x to the 6th, and it's also going to give me the right middle term. To get 8, we could do that with a 2 times a 4, or a 4 times a 2, or a 1 and 8, or 8 and 1. So we have to list out all those possibilities. Now to see which one it is, we're going to check our outers times our inners. 3 times 4 is 12. 2 times 1 is 2. Can I get 14 out of 12 and 2? I can. If I make them both negative, then I'll get my negative 14. So I need minus signs for both of these. So we got it to work. It's going to be 3x cubed minus 2 times 1x cubed, or just x cubed, minus 4. Because these are higher powers, you just want to do a really quick check to see if maybe these could factor some more. Unfortunately, because of those x cubes, the only way they might factor is if they were differences of cubes, and 4 is not a perfect cube, 2 and 3 are not perfect cubes, so this isn't going to factor any further. So we are finished. Okay, the next 2 examples here have variable powers. Notice we have a y up there in that power. So when we first look at the problem, again, look for that GCF, which there is none because there's no leading coefficient out front. And because we have 3 terms, the only other method left to try is reverse FOIL. So that's what I'm going to try. We get a little bit lucky here because the leading coefficient is a 1. This should be the easier case. I won't have to do all that trial and error. Now, how do I multiply, or what do I multiply to get k to the 2y? Look at that middle variable to give you a clue. If I put k to the y here and k to the y here, remember that k to the y times k to the y, using laws of exponents, you add the powers if you're multiplying the bases. So y plus y is 2y, which is exactly what we wanted. So k to the y is the right choice. So whatever variable you see in the middle term is what you're going to need to have in these front two positions. So I have k to the y times k to the y is k to the 2y. Now I need two numbers that multiply to negative 5 and at the same time add to a positive 4. Well, the only way to get 5 is 5 times 1, and if I want a plus 4 in the middle, I'm going to make the bigger number, the 5, positive, and the smaller number, the 1, negative. And that way, plus 5 minus 1 adds to positive 4. So we got our solution, k to the y plus 5 times k to the y minus 1. Okay? On the next example, we look across, we've got 3 terms, so it looks like maybe reverse FOIL, but before we jump into that, these powers on the y's are pretty high, and if you look at the coefficients, 30, 26, and 40, those are all even numbers, so at the very least 2 is going to go into everything. So there is a GCF here first. Pull that GCF out first before you do anything else. So if I think about 2 goes into 30 15 times. 15 isn't going to go into these other numbers at all, so 2 is the biggest number that I can pull out. In terms of the y's, each of these terms has a y. We have a 7a power, 6a power, and a 5a power. What's the smallest power that you see up there? It's the y to the 5a. So your GCF is going to be a 2y to the 5a. In parentheses, let's write down what we're left with. 2 goes into 30 15 times. If I pull out 5 a's and I had 7 a's to begin with, how many a's are left? 2 a's. And if you double check, 5a plus 2a gives you back that 7a. In the middle term, I have a minus sign. 2 goes into 26 13 times. And if I pull out a 5a plus what gets you 6a, I need one more a. So if I take away 5 a's from 6a, I need 1a left over. And for the last term, 2 goes into minus 40, negative 20 times, and I pulled out all of these 5a's, so there's no y's left over. So we pulled out our GCF. Now what we're left with is a trinomial, 3 terms, so you can't stop here. You are going to have to recopy your GCF and see if, because we have 3 terms, reverse FOIL might work on what's left over. So we have to try it out. So in the front position, we need 2 things that multiply to 15y to the 2a. So in terms of the variable, look at the variable in the middle. That's the clue to tell you what variable you need in these front positions. I need y to the a times y to the a to get y to the 2a. I also need 2 numbers that multiply to 15. There's a couple choices for that. 3's and 5's or 1's and 15's. On the end, I need 2 numbers that multiply to 20. That could be 4's and 5's, 2's and 10's, or 1's and 20's. So there's several choices for that. Since 15 had only 2 choices, I'm going to choose 3 times 5, and hopefully that will work. And to get 20, I could do 4 times 5, 5 times 4, 2 and 10, 10 and 2, 1 and 20, or 20 and 1. We're going to check our outers and our inners to see which ones work. So 3 times 5 would be 15. 4 times 5 would be 20. Can I get a 13 out of a 20 and a 15? No. So this choice doesn't work. So we go to the next choice. 3 times 4 is 12. 5 times 5 is 25. And 25 minus 12 is 13. So this looks like it's going to work. I actually want a negative 13, so the bigger number here needs to be negative. So that means the 25 should be minus, the 12 should be plus. The 25 came from this 5, so I'm going to put a minus in front of it. And the 12 came from this 4, so I'm going to put a plus in front of that. So we have our solution. final answer, don't forget your GCF comes down 2y to the 5a, parentheses, 3y to the a minus 5, parentheses, 5y to the a plus 4. That was a very long, tough problem, very challenging, but it's doable as long as you break it down and check all of your different factoring methods. Okay, on our next example, we have the quantity h plus k squared minus 9. And this first term, h plus k quantity squared, is obviously a square because of that little 2, and then we're subtracting 9, and 9 is a perfect square. So we have a square minus a square, so this is going to be a difference of squares pattern. So in order to factor this, we're going to set up our two sets of parentheses. In the first position, we want whatever we would have had before we squared, so that's this quantity that's inside of the parentheses. So we're going to put an h plus k and an h plus k in these front two positions. And then in the second positions, we want two numbers that multiply to 9. That's square root of 9, so that's going to be 3 and 3. And to make it a difference of squares pattern, we want one to be plus and one to be minus. And that way we won't get any middle terms. So here is our final solution. On the last example here, we have 100m to the 2q minus 81, and we want to see what that equals. So in order to factor this, recognize that 100 is a nice perfect square, 10 squared. 81 is a perfect square, 9 squared. And because this power 2q is even, since it's being multiplied by 2, that makes it a perfect square as well. So this is also a difference of squares pattern. So in order to factor, we're going to write our two sets of parentheses. The square root of 100 is 10, so I'm going to need 10s in the front. The square root of 81 is 9. And for those variables, we need two things that multiply together to give us m to the 2q. So I need to have an m to the 1q and an m to the 1q. That way when I multiply m to the q times m to the q, we add exponents, q plus q gives me that 2q. And then to finish it off, to make it a difference of squares, one of these is plus and one of these is minus. And there is our final solution.
Okay, on this next example, we have some fairly large numbers, and we also have x's and y's in both of our terms. So that should be a clue that there's probably a GCF, so you want to check for that first. Using your calculator a little bit will help you see that 27 does divide in evenly into 216. 27 times 8 is 216. So I can pull out a 27. And then if I look at my x's, I have 5 here and 2 here, so you want to pull out the smaller of the two powers, which means I can pull out 2 x's, or an x squared. And then for my y's, I have 4 y's here and 1 y here, so I can pull out at most 1 y. So if I pull that out, in parentheses we're going to write what's left over. Now this 27 is gone. I pulled out 2 of my x's, so I should have 3 x's left, and I pulled out 1 of my y's, and I had 4, so I should have 3 y's left as well. And then from this second term, remember 27 times 8 is 216, so when I divide by that 27 and pull it out, I'll be left with this 8, and then I pulled out all of my x's because I pulled out 2, and I also pulled out my only y, so the only thing I should have left here is my 8. Now if you look at what's left, you always want to double check and see what's left and see if it factors any further. And this one does. And the clue to that is you've got some nice cubes here on the x and the y term, and 8 is a nice perfect cube. It's the same as 2 cubed. So this stuff in the parentheses is actually a difference of 2 cubes. And that means it can factor further, and we need to use our pattern in order to do that. So we're going to leave our GCF out front. It's done, but it needs to still be there. And then when we factor a difference of 2 cubes, remember there's going to be 2 factors. The first factor has 2 terms, and these first 2 terms come from the cube roots of what you started with. So the cube root of an x cubed would just be an x, the cube root of a y cubed would just be a y. And then the cube root of 8 is that 2. And since this is a minus inside of our original problem, our first factor will be a minus as well. The second factor comes from these two terms. In the first position, we're going to take this xy and we're going to square it. So we want to square both the x and the y. So that would make it an x squared, y squared. On the end over here, we want to square whatever we see in this position. So 2 squared would be 4, and that's always positive. Then the middle term comes from just multiplying these two together. So that would be a 2 times an xy, or just 2xy. And you always want the opposite sign from whatever you had in this first factor. So if this is minus, then our middle term needs to be plus, so that when we redistribute, all those middle terms will cancel out, and we'll only end up with the very first term and the very last term. So that completes our factoring. When you do a difference of cubes or a sum of two cubes pattern, this trinomial over here will always be prime. You won't be able to factor it any further. So you'll know that you can stop once you get to this point. So here is my final solution. Now the very last problem here is kind of a tricky one. It's probably not something you would ever think to do the first time you see this problem, but if someone shows it to you, then you'll be able to remember to try it again. Now this one does not have a GCF throughout all 4 terms here. There's not a number or a variable that goes into all of them. So we have to try one of our strategies. And because this has 1, 2, 3, 4 terms, normally when we see 4 terms, we try grouping. Unfortunately, when we try grouping, we normally do the first 2 terms and the last 2 terms. And you can see that these first 2 terms have a 4 and an x that you could pull out, but that's not going to leave you with anything in common with these 2 terms over here on the end. So that practice of grouping, where you try to pull something out and what you're left with should match, is not going to work on this particular problem. So that's what makes this one tricky. So what we're going to do is we're still going to do grouping, but we're going to do it in a slightly different way. Instead of grouping the first 2 and the last 2, I'm actually going to group the first 3 terms, because this is a pattern for the square of a binomial. And if you don't see that, just think about your normal way of doing reverse FOIL to factor this. We could do something times something to get 4x squared, and there's a couple ways that that could happen. You definitely need an x and an x, and it could either be a 4 and a 1 or a 2 and a 2. On the other end, I need to get a 1 on the end, and the only way to get 1 is 1 times 1. So if we try to fix our numbers in front of these x's, you can hopefully see that I would need a 2 times a 2 to get that 4x squared, and then in the middle I'll get a 2x plus a 2x, and when I make both of those positive, I will get that 4x in the middle that I want. So I can make both of these pluses, and that will make this factor into the first 3 terms of the original problem. Now notice that these 2 factors here are identical. So I'm going to rewrite this as 2x plus 1 quantity squared. And I'm going to think of that as a perfect square. That's why I said up here earlier that this is actually the pattern of a perfect square binomial, because it's 2x plus 1 quantity squared. So we factored these first 3 terms into this quantity, and we still have that minus y squared on the side. So now if you look at what we've ended up with now is a new pattern where we have something squared minus something squared, and that is a difference of 2 squares. So that means it factors further. It would factor into 2 sets of parentheses. In the front spot, we need something times something that will give us 2x plus 1 quantity squared. Well, that's just going to be 2x plus 1 times 2x plus 1. In the back, we need something times something that will give me y squared. So that's just going to be a y times a y. And in order for those middle terms to cancel out, and in order to be a difference of 2 squares, you need one of these to be plus and one of these to be minus. So my final answer is 2x plus 1 plus y and 2x plus 1 minus y. Okay? So if you have 4 terms, and that would lead you to try grouping, but you can't get it to work by doing 2 and 2, then sometimes, very rarely, but sometimes you might need to group the first 3 terms together and rewrite that as a square so that you can use your difference of squares pattern. All right, that concludes our lecture on factoring. Good luck.